Hello everyone, my name is Dhanya Chowdary Arimilli and I'm a student at Indus International School, India. Last summer, I had the honor of being part of the CCIR Future Scholar program where I pursued a research intensive course titled Computational Economics and Social Science, Networks and Modeling of the Real World, under the mentorship of Dr. Daniel Cassis. Today, I'll be presenting my research paper, which investigates a unique intersection of network theory and sustainable development. This project integrates economics, data science, and public policy, all to better understand the systematic factors behind India's clean energy transformation. India is one of the leading nations in the global energy landscape. However, we face the twin challenge of meeting soaring energy demands while also mitigating climate change. India has made a bold commitment to reach net zero emissions by 2070, and more immediately, to achieve 500 gigawatts of non fossil fuel based electric power capacity by 2030. While these national level commitments are clear, there exists significant disparity among Indian states in their transition to renewable energy. Some states, like Karnataka and Gujarat, are trailblazers, while others are clearly lagging behind. This raised a fundamental question in my mind. Why do some states adapt to renewable energy faster than others? Traditional answers point to factors like natural resources or political will. But I hypothesize that there's something more structural at play. A state's position in India's trade and transport network, which could directly affect its access to technology, capital, and infrastructure. That's what led me to this study. The central research question of my study is to what extent does network centrality influence renewable energy adoption across Indian states and union territories? I hypothesized that states with higher centrality in the interstate trade network are more likely to have a higher renewable energy index. This grounded in economic theory, which suggests that central hubs tend to attract more investments, enjoy better infrastructure, and benefit from policy spillovers. In other words, being well connected isn't just about trade, it can catalyze sustainability too. To understand the urgency of this topic, let's look at three important facts. As of 2024, only 22% of India's total energy production comes from renewable sources, despite its ambitious goals. The government aims to achieve 50% of installed electricity capacity from non-fossil fuels by 2030, which will require massive infrastructural changes. Meanwhile, coal still powers around 70% of India's electricity generation. These figures illustrate the gap between ambition and reality. Trade within Indian states is not just a matter of economic output, it's the backbone of regional development, resource flow, and state level infrastructure evolution. According to a pivotal 2019 report by the Reserve Bank of India, states with higher trade openness demonstrate more stable economic growth, increased infrastructure environments, and a stronger fiscal position. This isn't just a financial correlation, it's a structural reality. Trade promotes access to resources, greater exposure to innovation, and faster diffusion of technology, all of which are key to renewable energy growth. Building on this, we also look at Chakrabarti and al's, who found that in Kolkata, one of the major cities in India, neighborhoods with higher transportation network centralities also command higher housing prices. This was a proxy for how infrastructural connectivity translates to economic premium. Applying this logic to a state level trade network, one can infer that Indian states with higher centrality, especially those central to interstate trade, may benefit not only from logistics but also preferential access to renewable energy technologies. Now, let's add a policy perspective. Barbosa and al. Argue that central regions in trade network bear a dual responsibility. They received disproportionate benefits, but also have the moral and structural responsibility to lead sustainability and trade. This means high centrality states like Gujarat or Maharashtra aren't just natural leaders in renewable energy, they should be strategic enablers of green change across India. Further, Iyer and Jha argue that states with advanced trade networks can support grid transformation and large scale energy parks due to better policy coordination and technological bases. Last but not least, the AMBER and IEEFA Electricity Transition Report draws attention to regional disparities in renewable energy adoption. That gap is what my research aims to address by connecting trade centrality with renewable transition metrics. To build this network analysis, I first needed robust and granular data on interstate trade. For this, I accessed the 2019 to 2020 DGCIS data from the Government of India, specifically tables 4, 5, and 7, which were goods by air, goods by rail, and goods by water, respectively. The diversity of transportation modes helped me capture a comprehensive picture of how states are not just connected through traditional railways but also air and waterways. This multiple trade dataset ensured that even remote and peripheral states had some representation in the network. Each record listed a trade flow between two states, including the weight and direction. I aggregated the trade flows across all three modes to calculate a total trade weight for each state and union territory. This sum was then used as the weight at the edge between each pair of the network graph. By doing this, I was able to generate a weighted directed graph using NetworkX, a Python library that specializes in complex networks. On the energy side, instead of relying on just one metric like energy consumption, I built a composite transition to renewable energy index using three carefully selected metrics from the Ember report. The first one is renewable energy mix and consumption, which reflects how much renewable energy a state currently uses. And then the second one is utilized renewable energy potential, which measures how well a state is using its assessed renewable energy capacity. And the third is public EV charging stations, representing the infrastructure dimension of the transition. Each of these metrics reflect a different dimension: current progress, untapped potential, and infrastructural availability. By averaging these three indicators, I created a balanced index that captures how seriously a state is moving towards renewable energy. Once the trade flow matrix was finalized, I visualized it as a weighted directed network graph using NetworkX. Here, each node represented a state or union territory, and each edge represented the total trade volume from one state to another. Each of these tables provides structured and clearly labeled data on the amount of goods traded between state pairs. Moreover, combining trade by rail, river, and air allowed me to capture multidimensional interactions, not just most frequent or obvious ones like highways. This approach added completeness and robustness to my model. To prepare this data for network modeling, I summed the total volume traded between every possible pair of Indian states and union territories. A higher trade flow meant a thicker and darker line or weight between each trade state or union territory, making visualization intuitive and informative. Edges were then formatted using a radial arc layout, preventing them from overlapping and improving readability. The edge labels were shortened using notations like 1M to denote 1 million units, which avoided clutter and retained scale. Next, I obtained a shapefile from UC Davis to position nodes on a realistic Indian geographic map. Using GeoPandas, I paraphrased this file and matched each node to the corresponding state or union territory coordinates. In case where the shapefile lacked data, like Chhattisgarh or Lakshadweep, I inserted manual coordinates based on external graphic inferences. To further enhance readability, I applied a non-linear scaling transformation to the x and y coordinates. Specifically, the x values were centered relative to their mean, and the y values were scaled using a power law function. This made dense clusters more legible and spaced out the graph while retaining the recognizable shape of India. The final visual network was color coded by region: South India, Northeast, Central, Northwest, and Union Territories, allowing viewers to instantly see geographic clustering. A custom legend helped decode the color and edge thickness. For analysis, I computed two types of centrality: degree centrality, which measured the number of direct connections a state had, and the eigenvector centrality, which evaluated a state's influence by looking at the importance of its neighbors. This aligns with the power centrality theory, which emphasizes that being connected to influential nodes carries more power than just being connected to many nodes. For instance, even if a state like Odisha had fewer trade connections, its high eigenvector centrality stemmed from its links to influential states like Maharashtra. Conversely, Punjab's many trade links don't result in a high eigenvector centrality score because its partners were less influential. To move from visualization to analysis, I started with the Pearson's coefficient. Using the dot curve method in Python, I calculated the linear correlation between eigenvector centrality and the transition to renewable energy index. The result was a moderate positive correlation of 0.412. This tells us that states with higher centrality in the trade network tend to score higher in renewable energy readiness. Next, I performed a simple linear regression using the ordinary least squares method from the stats models library. The regression equation was as shown on the slide. You may wonder why 1020 seems so high. That's because the eigenvector centralities are often tiny decimal values. A small change in centrality, let's say 0.01, results in a meaningful increase about 10.2 units in the renewable energy index. This makes the slope more interpretable. The R squared value of 0.17 shows that around 17% of the variation in the transition to renewable energy index can be explained by the eigenvector centrality alone. While not very high, this is meaningful in a complex system like energy policy where multiple variables also play roles. First, we must recognize that renewable energy creates positive externalities, spillover benefits to third parties such as clean air, better public health, and reduced climate vulnerability. However, without proper pricing, these benefits remain underprovided in a free market. That's what's called a market failure. High centrality states like Maharashtra or Tamil Nadu have access to capital and coordination, so they're in a better position to internalize these externalities using mechanisms like the Pigouvian tax, subsidies, or renewable energy quotas. But peripheral or less central states like Tripura or Lakshadweep lack both market size and fiscal bandwidth, making state intervention necessary. Another key issue is regional inequality. Trade centrality isn't equally distributed, and neither is renewable energy access. Central states get richer and greener, while peripheral ones lag. This fuels the positive feedback loop of inequality. To address this, we can apply tools like carbon taxes or non renewable sources to discourage dirty energy, tradable permits for emission caps, and government investment in green infrastructure, particularly in the lagging regions. All of these policies tie back to the idea of allocative efficiency and equity. This research helps identify which states need intervention and which can lead the change. Here are some key policy recommendations. Let's begin with states that are already central, like Gujarat, Maharashtra, and West Bengal. They need to not only sustain the renewable energy transition, but also act as influencers. These states should invest in grid extensions to share surplus renewable power, energy storage systems, and policy knowledge to guide weaker states. Then we look at outlier states, especially most of Northeast India. My findings show that these regions are both peripheral in trade and lagging in renewable energy adoption. The solution here lies in interstate partnerships, shared polar parks, and coordinated EV infrastructure and pooled financing models. Union territories and island states like Lakshadweep and Andaman and Nicobar Islands have unique challenges. For them, the government can focus on localized solutions like microgrids, floating solar farms, or even hybrid solar wind setups. Then there's an exciting opportunity cross border renewable corridors. West Bengal and Tripura, for example, are already part of the BBIN initiative, a multi nation grid across Bangladesh, Bhutan, Nepal, and India. These corridors can elevate trade centrality and serve as a green energy pipeline. Finally, I propose smart infrastructure investments, which are AI driven demand response systems, predictive maintenance for solar grids, and IoT based energy meters. All these can ensure that states with high centrality also have technical strength to lead. Despite the strength of this model, there are limitations. Firstly, my analysis focuses only on interstate trade via rail, river, and water. This excludes other key flows like highways, electricity exports, and pipelines, which may change the centrality rankings. Second, renewable energy index is only based on three indicators, while others are balanced. There's more than transition, such as rooftop solar adoption, investment trends, and grid reliability. Third, my model doesn't control for confounding factors like political will, state specific policies, and natural resource availability, as well as climate conditions. For example, a state may have high centrality but low solar potential due to cloudy geography. In the future, I aim to add multivariate regression with more independent variables, a time series analysis to check if centrality leads to renewable growth over time, as well as spatial modeling to explore clustering effects, particularly using network analysis tools like network entropy. To conclude, this study has demonstrated that network centrality, specifically eigenvector centrality, has a meaningful influence on the pace of renewable energy adoption across Indian states. This reinforces a broader idea. The transition to clean energy is not just about resources, but also about relationships, how states are embedded in trade and grid systems. As India moves towards its 2070 net zero target, policies must reflect not only technical capacity, but also network influence. Thank you so much for your attention, and I'm excited to hear your thoughts or questions.
Awesome. Hey, Dhanya. Yeah, there are
So,
a few actually more policy related questions from the audience outside of the chat.
okay,
I guess I'll start with the first one, which is
sure.
how do interstate policy alignments, they said things like energy sharing or joint parks between states, like joint solar parks, how does that influence the network in your model?
So I think, as I already mentioned, when different states relate with each other, share their knowledge as well as their resources, obviously the trade between them will improve. And they also gather data from each other about how to actually use the resources that they already have and implement better strategies to get public attention as well as form public private partnerships in a better way so that the transition towards renewable energy, particularly in India, could be at a faster pace.
Got it. And I guess going along with that, um, were there any states with high renewable potential that scored lower in centrality because of like weak coordination with other states or weak policy or something like that?
Yes, there were a couple like that. I think the medium states like Telangana, Andhra Pradesh, they were really good at trade. However, they weren't exactly able to match up in their renewable energy scores. And then there's some that have really good potential for renewable energy, but are not able to match up in trade because of their geographic locations, like
Mhm.
most of the northeastern states of India.
Right. Yeah, I think the final question was about that. It was like, what are the major infrastructural barriers that keep the Northeast isolated or
I
less
think one
central?
is, yeah. So the one is definitely how peripheral they are within the map itself. So if
Mhm.
we look at this, right? So northeastern states like Tripura, Meghalaya, Assam, and all, so they're really peripheral to the rest of the country, which means that they're not trading as much. And it's also because of their geographic location itself. It's a very it's a lot of mountains, hills, etc. And adoption of renewable energy becomes really, really difficult there.
Right. Yeah, no, I can totally imagine, right? Especially like based on where the resources are coming from. Like if they're
Exactly.
more centralized, like it's harder just geographically to get to that location.
Hmm.
That was all the questions that were from the chat. I guess what's next for this work? It seems really inspiring, and like policy oriented. So do you have plans to share this or, like publish or what's next?
I do. I actually recently finished it like a couple months back, and then I just a week ago actually submitted for review at
Oh,
the
nice.
Scholar Research Journal. So I'm waiting on their update.
Awesome. And yeah, do you have plans to continue working in this field or, focused on kind of like relationships between Indian state government or, like what are you doing next?
I do. I actually want to pursue economics and data science in college. So I think I want to see where it goes from there and then maybe related to public policy as well.
Awesome. Well, thanks so much for presenting today. It was a wonderful presentation. And if there's anything else you have to say, please go for it.
And no, I think that's it.
Okay, awesome. All right. Well, thanks for your time.
And thank you for the opportunity.
Yep.